Hi, everybody. So Broadcom is just unveiling its third generation co-packaged optics platform, the Tomahawk 6 Davisson, delivering up to 102.4 terabits per second of Ethernet switching capacity for next-gen Ethernet clusters. This is definitely a major milestone in optical integration and power efficiency. Joining me here today is Manish Mehta and Rajiv Pancholy of Broadcom's Switch and Optical Systems Division to discuss how this technology is advancing. So welcome.
Thank you. Appreciate it. Thanks, Jim.
So Rajiv and Manish, the first question is on setting the stage, the need for CPO. Can you start by explaining a little bit about the scale of east-west AI traffic that we're seeing today and why traditional pluggables can't keep pace?
Sure. So, when we launched our CPO development efforts, and we announced that about 5 years ago, we really weren't developing with AI in mind. We were developing solutions for front-end cloud networks to replace kind of traditional optics, which had some challenges in how they were going to scale. But then what we found over the last few years is AI training scale-out networks just exploded the optical bandwidth requirement versus anything we had seen on front-end cloud. It was about an order of magnitude increase in optical bandwidth that was required per processor. And that has led to a significant increase in volume requirements and also a rapid increase in velocity on how quickly these new optical generations have to be released. Traditional pluggable optics are serving the need at the moment for sure, but they continue to increase in power generation over generation. They increase in complexity. The signal integrity challenges continue to become more difficult, taking signals that are 100 gig, progressing to 200 gig from the core ASICs out to the front panel. And CPO is a way of really densifying that technology and placing it very close to the ASIC to simplify the interconnect and reduce the need for complex signal processing and increase laser split ratios and improve upon a lot of the challenges that traditional optics are facing right now in meeting the needs of that training, east-west high radix scale out traffic.
Yeah, so it's been a really interesting evolution as well, right? As you've gone through the first, the second, and now here the third generation with the CPO and looking to see where that meets the market demand. You're on track with that now, you think?
Yeah, we're pretty excited about our third generation development. Our first generation was Tomahawk 4 Humboldt. It was our first development of CPO. We're very fortunate to have a lead partner who did some small scale deployments. It allowed us to build a manufacturing platform and start building a partner ecosystem in the supply chain to actually be able to ultimately scale CPO. Our second generation was Tomahawk 5 Bailey, and it's been a great story in being the first CPO ever in the industry to really get into multiple customer networks and customer environments and tested for reliability and link stability. And it also demonstrated or proved that we can hit the power targets that we were originally going for and the power improvements that we were targeting with CPO. So I think with Gen 3, with Tomahawk 6 Davisson, we now have a product that meets critical customer needs. It's high radix. It supports the 512 ports available off of Tomahawk 6, fully extracted optically. And it's, here and going to be kind of sampling to customers at a time that the next phase of training deployments are being architected. We're pretty excited about the timing of this release.
Yeah, it looks really exciting. Rajiv, could you perhaps walk us through some of the architecture and packaging that's gone into Davisson, and especially the capabilities that are being brought to bear from TSMC with its COUP technology?
The COUP process from TSMC is looking very good. The Davisson engine obviously has that, though that attach, is something that we've done on this Gen 3 Davisson. The platform that we're using leverages everything from our Gen 1 and Gen 2, the back-end processes, our OSATs, our assembly, our fiber attach, right? All of that, we've built upon and hardened. And touching on what you were saying earlier, we've been, we brought CPO out to compete on, power and cost and reliability versus pluggables. But, with this recent data from of our main end customer partners, it's really showing link stability. And that's something that translates into significant value as you start training these large AI clusters of GPUs. And now you don't have to go back to checkpoints, and you leverage kind of this robustness of the CPO platform, which really has significant value over any type of pluggable.
Let's talk a little bit more about that link flapping and reliability issue. I know you guys were quoting a big number, 1 million. What is it? 1 million hours of testing?
Yeah, so one of our customers, Meta, published a paper and a study where they stated that the first million device hours of operation of Tomahawk 5 Bailey operated link flap free. And that's a big deal, right? These, as Rajiv was mentioning, link flaps have been a sore point in the migration from sort of front-end cloud networking to AI training, where a link event doesn't have redundancy to be overcome. And you need to kind of go back to a point in that training job and restart, and that's loss of XPU or GPU utilization. So this was always one of our theories, that if you take silicon photonics and you take mature CMOS nodes, and you build optical engines using high volume, proven foundry and OSAT processes, and then you pair it with what we've now proven through our first two generations on back-end assembly and test, with soldered optical engines on a common substrate with an ASIC, that you can actually get silicon level performance and reliability for the optical interconnect versus the kind of traditional perspective on optical interconnect performance, which is, tends to be a discrete device, pluggable format. And this is the first evidence from a customer in their environment that that hypothesis is actually has a very strong foundation and is being proven in real hardware with real hardware.
And what exactly is the reason then? Is it because the packaging has hermetically sealed it in and you're not getting dust on the optics?
So it's a tightly integrated solution. While a normal pluggable transceiver, the components in the pluggable transceiver can operate very well on their own, but the pluggable transceiver is housed in a module that is inserted into a front panel of, let's say, a switch system or some type of ASIC system. It's inserted mechanically. There is variability system to system on the links, the electrical links from the, say, substrate through the PCB to the front panel. So you can have variability within a system between the different traces. You're going to have variability system to system on those traces, the design, the PCB vendors, the material systems. There's variability on the mechanical connectors. All of that just generates a lot of sources of variation on the link performance. And as the speed continues to increase, those challenges start emerging in larger pain points in training networks. Well, here you have a known good, what we call TP1 and TP4 link at manufacturing. During CPO testing, that electrical side link is defined, it's characterized, and so we think that's a really big reason why we're seeing significant improvement in the performance. So they also characterized it from something that, maybe a little more relevant for a broader networking audience who's not maybe in the details of like what's a link flap. One was that they, showed experimentally that the CPO serviceable failures are, 5x lower on this initial study than pluggable transceivers. And we think that's just going to continue to improve, right? We're still in the early days of CPO and we still have some things to work through. And then this is the very, I think, exciting one, which is MTBF improvement that they calculated to deliver a 90% training efficiency improvement for a 24K GPU cluster.
Interesting. So I want to go back to the power question because another really big item in your announcement is the number that's quoted, a 70% reduction in power compared to pluggables. Is that right? And how impactful is that in terms of building out these really massive AI data centers?
Yeah. Yeah, so it's real. We proved it on Bailey, where a traditional say 800 gig transceiver, at the time we released was operating at about 16 watts, and we hit our target of less than 5.5 watts. And that's really two things. You eliminate the DSP and you're running CMOS for your EIC. Because we're so tightly integrated, we can use pretty advanced CMOS nodes with low power consumption for the TIA and the driver circuitry. And we're expecting the same level of power savings for the Davisson generation as well. I think
Okay.
the value of this is certainly important over the long term. We fully recognize that in the short term, sites and racks are provisioned to support the pluggable transceivers, as they should be, because that's the known technology that's going to continue to deploy in very high volume. So in the short term, we think that it's really this link performance that is driving a lot of excitement and the next phase of adoption by end users. Over generations, as their comfort level and grows with CPO, I think you'll start to see more provisioning done with CPO in mind for power, and that could be very important in improving rack density of GPUs because you don't have to use as much power on the networking.
Yeah.
Rajiv, add to
And
that?
Jim, yeah, just to add to that, right? The data that Meta presented actually shows a 65% reduction between the CPO platform that they use, the 100 gig Tomahawk 5 Bailey, versus kind of 100 gig, 800 gig, 400 gig modules running at 100 gig per lane. So now as you move to 200 gig per lane, that's where we're saying, okay, look, it's 65, it's measured, you're seeing it now at 100 gig per lane. You should be in the 70s when you're at 200 gig per lane.
Right, right. Yeah, everything's moving faster and faster, which leads into my last question, kind of the look ahead and the roadmap ahead. Yeah, it seems like we're just 100 gig per lane and now 200 gig per lane. And before you know it, people are already planning 448 gig per lane, right? Is the CPO roadmap going to keep up with this? What do you guys see looking ahead?
We're certainly investing to make it keep up with that. So yes, we absolutely believe that CPO, high density silicon photonics integration, co-packaged optics, using a lot of silicon photonics and CMOS and advanced packaging techniques will be able to keep up with the bandwidth requirements of AI networking. And we've already announced that we're in development of our Gen 4 400 gig per lane CPO. And there's a lot of innovation required in these next generations, right? We're looking at increasing the split ratios of our lasers. We're looking at the next phase of kind of advanced packaging techniques. So we're pretty excited about not just releasing our Gen 3 Davisson program, but also what lies ahead for Gen 4 and just continuing to do what we can to innovate and do everything possible to make sure that optics are not the bottleneck for generational advancements in AI networking.
All right, fantastic. Lots of good innovations there. Thanks for this update. Really appreciate it.
Thank you.
Thanks, Jim.